Okay, we are back now to cover the model itself. So we already talked about how we are loading the data, and now let's see how the model is built. Okay, so the first thing is get into the model, and we are getting the model. We create the model based on the option we chose in the UI. Let's look first how it's done when using TensorFlow. And when you are building a dense model with TensorFlow, it is basically as simple as that. So we choose the layers, and you can see here what I talked about the images and how we manipulate the data. So here, when we are defining our shape on using TensorFlow, we kind of work on this two dimensional array, or actually three, because we have one here as well. But we immediately flat that three-dimensional array in one single dimensional array. You can see this is how it's done here, the flattening that I spoke. This is very that. So we define each layer. We define how many units or input size, basically this defining, and we define which activation function will be used for that layer. That's pretty much that. Let's see how it is on our vanilla neural net. Here, it is not much different. It's basically the same. We define layers as well, the same way we did with TensorFlow. The only difference here that we already start with the flattened size of the array. So here would be 28 by 28, and we define the first layer would be the size of the image itself, and you define relu the same way the same way we did for in the TensorFlow, and we say you have for our logic we define that's the input, and then we do the second layer the same way we did for in the TensorFlow. Now it is input size of the image and out size 42, relu as well, and now it's a hidden layer, and the output, it is basically 42 input. We have the 10 output, and use softmax this time. So what it is this 42? It's an arbitrary number. So that's part of the machine learning engineering. It is try to choose the right amount of neurons for your layer, and the amount of layers that we want to use as well. And the 10th here, it is basically the amount of options that we have in our images from 0 to 9, and to help visualize that a little bit better, we can go back to our course notebooks, and you can look at the vanilla implementation in Python, and you can see here that we are talking about those layers. So input layer and hidden layer. On this image here we work with two hidden layer, but in our example we just use one, so we'll be with this. Our architecture will be this. Another important thing to notice here, it is that the output, it is the amount of neurons that you're gonna have in our layer, and the same here, output 10. So here each one of this, it's a neuron, and it's represented by the output amount that you set. So in our case it will be 42 neurons on our layer, and 10 here, and here will be 7 to 8, basically. It's the size of the image. That's pretty much how we define our model architecture. So you can see there is not much difference from TensorFlow and from our implementation, and we can move ahead and see after we have let's see, when you create the model, if it is our own implementation, we just wrap in a model wrapper, and this model wrapper, it is just to have the same API independently of which model you are choosing. So we are gonna always set train, evaluate, and prediction. It will be always the same, independently of which model you are using. So you are handling which version we are using inside this wrap. Okay. So when you start training, so let me just go back to the model creation. When you work with TensorFlow, we have an extra step where it is compile, and then we just pass which the optimizer we are going to be using for let's say to reduce the loss and to improve the weights. And we also have here a metric, but it's not really necessary, and we are not covering on our in our implementation. So it's basically that. Then once you have the model itself, we call summary, and you have the same implementation hours. And then the most important part, when you have the model, we start to train the model with our data set, right? So let's have a look on how the training works. And the training start defining some byte size, so it's how we split the data and work in bytes. We also choose the number of epochs from the UI. Epochs, it's basically the amount of time that you are going to be training your model to the image. So basically we are going to be repeating the same loop over all the image multiple times, in our case 3 times. And so we just get the data, training data, and the test data. Test data is used to test our model in real time and give the feedback on the UI. And then we start the train itself. And when you are defining the train, so basically we pass the data and the label, and we also pass some callbacks, which it is the callback used to display real time the performance of the model itself. So it's just, this is used to display things on the UI. And you have 2 callbacks on batch for every batch, and 2 epochs. Epochs, it's times that you train our model against all the images. I think then let's see what it means to be trained under the hood. So if you are using TensorFlow, you just know that you need to define your 4D dimensional array tensors. So basically we take our images, and so basically do the images and set the height and the weights and how many channels you're going to be using, and the same for the label, and you just pass to the function called fit, and you don't know anything what would be under the hood of fit, what fit means. And that's why we have our vanilla neural network, because then you can see how things works under the hood when you are training. Right? And so let's see then, if you're not using TensorFlow, how it is, what takes to train a neural network. And then you can see it here. And let's see what you have under the hood when you are training things. First thing, you need to convert the flattened array. As I said, all the images will be in a single dimensional array, and you break that into multiple arrays of images and labels. And then we loop over the data, and if you see step here, it's basically a loop, and this loop is being triggered with this request animation frame. And why you're using request animation frame instead of a normal JavaScript loop, it is because we want to be interacting with the UI why you are looping. And if you do a normal loop, they will be blocking the UI thread. So I add the comment here. So you use request animation because we use the browser. Browser is triggering this loop, and therefore the JavaScript single thread can be looping over our training and also responding to the UI. So this basically this is very interesting thing, and when you are working with single threaded application, you need to take in consideration. And so you know that it's a UI, it's a loop, so therefore you have to kind of add some say some mechanism to keep the loop and see if you are looping over a batch or if you are looping over a epoch. And basically this is some mechanism to keep the loop and keep the state of the loop. And how things works, it's here that we really look at the fit of our vanilla neural network. And let's see what it is under the hood for fit. When you are training or fit it is a TensorFlow definition, but you could call this training as well. I just kept the same name with TensorFlow to easily identify which part of our vanilla network it is representing. Would be represented on TensorFlow. Okay, when you are talking about fitting, what you have to do basically 3 steps. We have to feed forward. Feed forward means go through all the layers, right? Passing to all the layers your input, and after we go all the way through your layers, you need to calculate the loss, and based on the loss, you would be the loss result, you'll be updating your internal weights. Okay, that's what means in a nutshell what means to train a neural network. So to make a little bit more of sense, let me open again the image represented our architecture, model architecture. And when I say feed forward, you are say I give my input data and do some process for this input data, and based on the weights that you have for each neuron, you want to be able to give a prediction of which image which number this image contain, right? And based on the output here, we compare with the real data. Let's say when you start training, you give the input and the label, right? And the output here would be compared against the label, and we see how far we are from the correct data, and that is the error loss that we're speaking, to see how far we are from the right answer. And based on this difference, we propagate back. So that's why you call back propagation. You propagate back through all the layers, and we calculate for each layer the error loss, and so on and so forth. And based on the error loss that we have, and based on the activation function that we are using, we do some calculation to update the weight towards more optimal values, right? Look at the code again. I think the code speaks by itself. So again, when you look forward, we are basically doing some calculation and trying to give a prediction. Then we see which the prediction was, and we calculate against the correct label. In our case here, we're calling target, and you see how far we are from the right answer, and we update our weights in order to have a better answer. It is basically these 3 steps. Based on two steps, we now know what means to be use backpropagation algorithm to train our neural network. In the next video, I'm gonna dive into each of these steps and see how it is done under the hood. Okay, see you in the next lab.